What if the most expensive fighter jet in history was destroying itself every single time it fired its own weapon? And what if the engineers who fixed that problem accidentally created something far more dangerous than the original design ever intended? That strange lump hanging under the belly of America's newest stealth fighter looks like a factory mistake. It looks like someone bolted a bathtub to the underside of a $110 million warplane and walked away pretending nothing happened. Aerodynamics experts wince when they see it. Radar engineers shake their heads. And defense analysts in Beijing, Tehran, and Moscow stare at satellite imagery of it, wondering why the most funded military on the planet left such an obvious blemish on its flagship aircraft. But here is what nobody is saying out loud. That ugly bump is not a flaw. It might be the single most brilliant tactical decision made in fighter aviation in the last 20 years. And once you understand what it actually does, you will never look at stealth warfare the same way again. If you want to understand the real engineering behind the machines that shape global power, do this right now. Smash that like button. Subscribe to this channel and turn on notifications so you never miss the next deep dive. And if this video changes how you see something, share it with one person who needs to hear it. Let us get into the story. To understand why engineers deliberately bolted an external gun pod onto a stealth fighter designed to be invisible, we need to rewind to a war that taught America a brutal lesson it has never forgotten. The skies over Vietnam in the mid-1960s were supposed to belong to missiles. The smartest minds in the American defense establishment had reached their verdict. The dogfight was dead. Guns were ancient relics. The future of air combat belonged to guided missiles that would destroy enemy planes from miles away, long before any pilot ever saw his opponent's face. The platform chosen to prove this theory was the F-4 Phantom II, a twin-engine monster capable of hauling nearly 19,000 pounds of weapons across 9 external hardpoints. It was fast, it was massive, and it bristled with the latest heat-seeking and radar-guided missiles America could produce. But the designers made one catastrophic decision. They removed the onboard cannon entirely. No gun, no backup, just missiles and confidence. In the sterile logic of a Pentagon briefing room, this made perfect sense. The math supported it. The simulations backed it up. But the skies above North Vietnam did not care about simulations. When American pilots found themselves tangled in close quarters combat with nimble North Vietnamese MiGs, the theory collapsed in spectacular fashion. The AIM Ibrit 9B Sidewinder, America's primary heat-seeking missile, had a maximum effective range of about 3.5 miles. That sounds reasonable until you hear the full picture. The infrared seeker could track moving targets at an angular rate of just 11 degrees per second. If the enemy pilot pulled into even a moderate evasive turn, the missile lost lock and drifted harmlessly into empty sky. Worse, the Sidewinder demanded that the attacking pilot position himself directly behind the hot exhaust nozzle of the enemy jet. In a chaotic furball of twisting, turning aircraft, getting perfectly aligned behind someone's tailpipe was nearly impossible under real combat stress. The AIM-7 Sparrow, the radar-guided alternative, was arguably even more dangerous for the pilot using it. It required the shooter to keep his nose pointed directly at the target for the entire flight duration of the missile. In a combat zone, crawling with anti-aircraft fire and enemy fighters, flying straight while holding a radar lock was essentially asking to be killed. Its minimum engagement distance sat between 2 and 10 miles. The rules of engagement demanded visual identification before firing, and the real-world probability of a kill dropped below 10%. These were supposed to be the weapons that replaced the gun. They could barely hit anything at all. American pilots suddenly found themselves in close-range knife fights with enemy fighters that were smaller, faster, and flown by pilots who had spent years training specifically for that kind of close-quarters combat. And the Americans had no gun to fight back with. The frustration of men like Navy pilot John Cheshire, who found himself in the merge with MiGs and realized he had nothing but unreliable missiles and no cannon, forced a crisis that could no longer be swept under the rug. The Phantom was rushed back to the factory. An external gun pod was bolted on first, and later an internal M61 Vulcan rotary cannon was installed. But by then, pilots had already died because someone in an air-conditioned office decided that guns were obsolete. The lesson was burned into institutional memory with the heat of lost pilots and shattered expectations. Every engineer in the American aerospace industry made a solemn promise. No American fighter jet would ever leave the production line without a built-in gun again. That promise became sacred law. When the Joint Strike Fighter program requirements were locked down in the early 2000s, the inclusion of an onboard cannon was treated as untouchable. The specifications demanded the ability to destroy lightly armored ground targets at ranges up to 2,700 meters. The weapon selected for this mission was the GAU-22A, a 4-barrel rotary cannon in 25mm caliber manufactured by General Dynamics. This thing weighs around 230 pounds and fires 3,300 rounds per minute. That translates to roughly 55 high-velocity projectiles leaving the barrel every single second. The ammunition used is the CT round, an armor-piercing semi-incendiary shell specifically designed to punch through steel plating and ignite whatever it finds on the other side. Muzzle velocity exceeds 3,500 feet per second, more than 3 times the speed of sound. Each round arrives at the target before the sound of the shot that fired it ever reaches human ears. But here is where the tension enters the equation. The total ammunition supply is just 220 rounds. The fire control system strictly limits each burst to about 35 rounds to prevent the barrels from overheating. That gives the pilot somewhere between 5 and 6 trigger pulls before the gun runs completely dry. Every burst has to count. There's absolutely no room for wasted shots. The F-35 compensates for this by integrating the gun aiming system directly into the pilot's helmet-mounted display through the active electronically scanned array radar. Wherever the pilot looks, the gun follows. The targeting data overlays onto the visor in real time, showing exactly where the rounds will land. It is technology that sounds like science fiction, but none of it matters if the aircraft tears itself apart every time the trigger gets pulled. When the GAU-22A fires, it generates a recoil force of approximately 16,500 newtons. To put that in human terms, imagine a small jet engine running in reverse inside the aircraft, slamming the entire machine backward with every single burst. That is an extraordinary amount of energy to channel through a structure that also needs to remain radar invisible and aerodynamically clean. The physics of this situation created a problem that no simulation predicted and no designer wanted to admit. On the F-22 Raptor, this force is handled gracefully because the gun sits at the root of the wing, inside the strongest structural section of the entire airframe. The wing spars and internal ribs absorb the recoil the way a thick concrete wall absorbs a punch. The energy disperses harmlessly through the bones of the aircraft. No damage, no vibration, no degradation over time. A clean solution. But on the F-35A, the Air Force variant, the engineers chose a different path. The GAU-22A was mounted inside the left shoulder of the fuselage, behind a small retractable door that pops open milliseconds before each firing pass. On paper, this was the elegant solution. It preserved the stealth lines and kept the weapon completely hidden from radar. In the unforgiving reality of mechanical physics, it created a slow-motion disaster. Every time the gun fires, those 16,500 newtons of recoil energy travel directly through the longitudinal beam that forms the structural spine of the fuselage. That beam carries aerodynamic loads, supports the wiring harnesses and avionics racks, and provides the skeleton over which the radar-absorbing composite skin is stretched and bonded. That composite skin was engineered to defeat radar waves. It was never designed to withstand repeated high-frequency mechanical shock from a weapon producing the recoil equivalent of a small rocket motor. And so what happened next was entirely predictable to anyone who understands how composite materials behave under sustained stress. The skin began to develop microfractures. The stealth coating started to crack and delaminate around the gun mounting points. With every additional firing session, the damage crept deeper into the structure. The radar cross-section, the single most critical attribute of any stealth fighter, started to degrade silently, invisibly, and persistently. Pentagon annual evaluation reports produced between 2019 and 2023 documented this in stark, uncomfortable terms. The F-35A's internal gun was classified as inaccurate and operationally unsatisfactory. The vibrations generated by firing were severe enough to misalign the targeting system and accelerate fatigue in the surrounding composite panels. Usage restrictions were imposed on operational squadrons. Pilots were told to limit live-fire training exercises with their own aircraft's primary weapon. The Air Force was essentially informed that using the gun on their $110 million stealth fighter might damage the very stealth capability the aircraft was built to provide. Think about that paradox for a moment. A gun that was mandated because of the blood-soaked lessons of Vietnam, installed at enormous cost and engineering complexity, could not be safely fired without risking the structural integrity of the jet it was supposed to defend. I want you to really sit with that for a second, because the story gets even more interesting from here, and I want to make sure you're paying close attention. If you are finding this as fascinating as I think you are, take a moment right now to drop a like on this video. It genuinely helps the channel grow and tells the algorithm that this kind of deep technical content deserves to be seen by more people. And if you have not subscribed yet, what are you waiting for? Hit that button and join this community. Now let us keep going, because what happened next changes everything. Turn your attention to the other two variants of the F-35. The F-35B, flown by the United States Marines, and the F-35C, built for carrier operations with the Navy, ran into a completely different wall. They simply did not have room inside the airframe to put the gun anywhere. The F-35B requires a massive vertical lift fan in the center of its body to perform short takeoffs and vertical landings. That fan consumes enormous internal volume. that would otherwise be available for weapons, avionics, or structural reinforcement. The F-35C must carry over 20,000 pounds of internal fuel to achieve the range demanded by long-duration missions over open ocean. Every cubic centimeter inside both airframes was already spoken for. There was no space left for a cannon and its mounting hardware. The problem was handed to a Danish defense company called Terma, known throughout the industry for creative aerospace solutions. And what Terma produced did not just solve the space problem, it fundamentally altered the strategic balance of modern naval aviation. They created external gun pod systems, designated the GPU-9A and GPU-8A, cylindrical housings built from carbon fiber composite that mount on the centerline weapon station directly beneath the aircraft's belly. To a casual observer, these pods look wrong. They shatter the smooth stealth profile of the airframe. They add measurable aerodynamic drag. They slightly enlarge the radar return. And they impose a significant penalty on transonic acceleration performance. The numbers tell the story clearly and honestly. The F-35A, with its internal gun, needs roughly 8 additional seconds to accelerate from Mach 0.8 to Mach 1.2. The F-35B, carrying its external pod, requires 16 extra seconds, and the F-35C, the Navy variant, demands an astonishing 40 additional seconds to push through the sound barrier. 40 seconds. In modern air combat, 40 seconds is an eternity. It is enough time for an enemy missile to close its distance. It is enough time for the tactical advantage to flip entirely. A pilot who needs those 40 seconds to escape a threat does not have them anymore. So why would the Navy and Marines accept such a steep performance penalty? Why would experienced military planners sign off on an installation that makes their flagship fighter measurably slower in the most critical phase of air combat? Because the external pod does something the internal installation simply cannot. It completely isolates the recoil forces from the airframe itself. When the GAU-22A fires inside the Termapod, all 16,500 newtons of recoil energy are absorbed by the rigid carbon fiber housing of the pod itself. That energy transfers into the centerline hardpoint, the single strongest mounting station on the entire aircraft, positioned directly beneath the main structural spine. Not one shockwave reaches the composite outer skin. Not one vibration penetrates into the avionics bays or the weapons compartments. The stealth coating remains completely undamaged. The targeting system stays perfectly calibrated. The airframe remains structurally sound across thousands of firing events over the aircraft's entire service life. Defense engineers refer to this approach as the sacrificial capsule philosophy. You accept a visible, measurable penalty in speed and radar signature in exchange for an airframe that fires its weapon without destroying itself. You trade aesthetic perfection for structural survival. You give up precious seconds of acceleration to gain thousands of clean firing passes without a single crack forming in the fuselage or a single coat of stealth paint flaking off the surface. It is the kind of trade-off that looks terrible on a specification sheet and works brilliantly on a battlefield. But the genius of the Termapod extends far beyond simply carrying a gun. This is the part that truly keeps defense planners in Beijing and Moscow awake at night, staring at classified briefings they wish they did not have to read. The pod is modular. Danish engineers designed the housing so that the internal volume, occupied by the GAU-22A, can be completely stripped out and replaced with entirely different mission systems, all while maintaining the exact same external shape and aerodynamic profile. The flight computer requires no recalibration. The drag characteristics remain identical. The pilot notices absolutely no difference in handling or performance. But inside that carbon fiber shell, the entire mission capability of the aircraft transforms into something completely different. Pull the gun out and install an advanced electronic warfare suite. The F-35 instantly becomes a flying jammer, capable of flooding enemy radar receivers with overwhelming interference and blinding entire air defense networks across a wide operational area. Surface-to-air missile batteries that depend on radar guidance suddenly cannot see what is coming for them. Replace the electronic warfare package with long-range reconnaissance sensors and signals intelligence equipment. And the fighter becomes an intelligence-gathering platform, mapping enemy radar positions, communication nodes, and command infrastructure while transmitting real-time targeting data back to the fleet. Mount a directional data link system inside the pod, and the F-35 becomes a command hub for autonomous drone swarms, coordinating dozens of unmanned vehicles deep into hostile territory while the manned aircraft stays at a safe standoff distance, never exposing itself to direct fire. And perhaps the most provocative possibility of all, the housing has been evaluated as a platform for compact directed energy weapons. Imagine a laser system hidden inside that unassuming belly pod, capable of burning out the infrared seekers of incoming missiles, disabling small, fast attack boats, or blinding enemy sensor arrays without firing a single conventional round. No ammunition expenditure, no acoustic signature, no radar trace of a weapon launch. The aircraft that everyone dismissed as carrying an ugly external lump turns out to be the foundation for weapons that most nations have not even begun to develop yet. Meanwhile, the F-35A is permanently locked in. Its internal gun bay cannot be swapped for electronic warfare equipment without a complete structural redesign of the fuselage. The Air Force variant is committed to a single configuration for the foreseeable future. It will carry its internal gun, with all its vibration problems and structural consequences, for the entire service life of the airframe. The Navy and Marine variants, forced by the lack of internal space to accept the external pod, accidentally gained the most flexible and adaptable fighter platform ever built. In the history of military aviation, they stumbled into superiority because they had no other choice. This modality has begun reshaping how the United States projects military power across the Pacific Ocean. Amphibious assault ships, vessels originally designed to carry Marines, helicopters, and landing craft, are being converted into what the Navy now calls lightning carriers. Ships like the USS Tripoli can embark up to 20 F-35B fighters, each equipped with a thermopod configured for whatever mission the tactical situation demands on any given day. These ships lack the catapults and arresting gear of a Nimitz-class supercarrier. They do not photograph well next to a 70,000-ton nuclear-powered flat top. But with 20 stealth fighters aboard, each capable of switching between ground attack, electronic warfare, aerial reconnaissance, and drone coordination simply by changing the contents of its belly pod, these lightning carriers represent a fundamentally new kind of naval power projection. They deploy faster, operate in shallower waters closer to shore, cost a fraction of a supercarrier, and present any adversary with a nightmare of targeting uncertainty. You cannot plan a defense against a carrier group when every fighter in that group might be carrying a completely different mission package from one sortie to the next. If you have made it this far into a video about structural engineering, recoil physics, and modular weapon systems, you are part of a very small and very dedicated group of people who genuinely care about understanding the real mechanics of global military power. I respect that deeply. Take 1 second right now and make sure you are subscribed to this channel with notifications turned on. You do not want the algorithm burying the next video from you, because what we cover here goes places that mainstream media does not have the technical expertise to reach. And if you know someone who is into defense technology, aviation engineering, or geopolitical strategy, send this video their way right now. Text it, email it, post it on your story. Every share helps this channel reach more people who think the way you do. For China, which has spent 2 decades and hundreds of billions of dollars constructing an anti-access and area denial network specifically designed to keep American supercarriers beyond striking distance of the Chinese mainland, the lightning carrier concept is deeply and fundamentally destabilizing. Those defense networks were calibrated to detect, track, and engage a small number of high-value carrier targets following predictable operational patterns. The entire system was built around the assumption that the United States would deploy 2 or 3 supercarrier strike groups into the Western Pacific, and that those groups could be targeted with long-range anti-ship ballistic missiles. Suddenly, the People's Liberation Army faces the prospect of 5 or 6 smaller, more dispersed aviation ships, each carrying stealth fighters that might be configured as electronic warfare platforms one sortie, autonomous drone controllers the next, and conventional strike aircraft the mission after that. The targeting mathematics that China spent 20 years perfecting starts to crumble. For Iran, which depends on layered coastal missile batteries and dense air defense networks to control the Persian Gulf and the Strait of Hormuz, the threat is equally disorienting. An F-35B configured with an electronic warfare pod can systematically degrade the radar coverage that those missile batteries depend on for tracking and engagement. A follow-up strike package carrying conventional gun pods and precision munitions can then engage the now blinded defenses from vectors they were never designed to protect. And the entire operation can launch from a flat-deck ship that Iranian intelligence services might not even classify as a carrier. The fog of uncertainty multiplies. The cost of miscalculation skyrockets. And the carefully constructed defensive perimeters that Tehran relies on begin to look more fragile than they ever have. The lesson embedded in this entire story is one that military history has been teaching over and over again, generation after generation, war after war. The elegant solution and the effective solution are not always the same thing. Sometimes they are not even close. The F-35A represents the perfectionist approach to engineering. Hide everything inside the airframe. Make the surface seamless and invisible. Trust the simulations and the design specifications. Believe that if the math works in the model, reality will cooperate. And when reality pushes back, when the physics of recoil and material fatigue refuse to conform to the optimistic predictions, the damage accumulates in silence. Cracks form where nobody inspects. Stealth coatings degrade away from public view. And classified reports stack up in filing cabinets, while the program office continues to insist that everything is on track. The F-35B and F-35C represent the pragmatic approach. We ran out of room. We did not have space to fit the gun inside. So we put it outside, we accepted the drag, We accepted the visual imperfection, we accepted the speed penalty, and in return, we got an aircraft that fires its weapon without cracking its own skeleton. We got a platform that can carry a cannon today and an electronic warfare suite tomorrow. We got a fighter that adapts to the mission instead of being permanently locked into one role for its entire service life. We got flexibility that no amount of internal engineering could have provided. History, from the jungles of Vietnam to the engineering laboratories of the F-35 program, has consistently rewarded the pragmatists. The gun matters. It always mattered. It mattered when John Chizire was in the merge with no cannon. It mattered when the Phantom came home with holes in its fuselage and no way to fight back. And it matters now on the deck of the USS Tripoli with 20 F-35Bs sitting in a row, each one carrying a pod that lets it shoot without breaking itself. But the gun only matters if the aircraft can survive using it. And the aircraft that survives is the one designed with enough humility to accept a solution that looks imperfect on a poster, but works flawlessly where it counts. Now I want to hear what you think. Look at this engineering trade-off and tell me in the comments below. Was mounting an external gun pod on a stealth fighter an act of tactical brilliance, or was it a bandage covering a fundamental design failure that should have been caught from the beginning? Type the word brilliance or the word band-aid in the comments and defend your position with everything you have got. I will read the best technical arguments and pin the most insightful ones to the top of this comment section for everyone to see and debate. That lump hanging under the belly of the F-35 is not a mistake. It is a scar earned by pilots who flew into combat without the weapons they needed to survive. It is a solution born from the honest admission that sometimes there is not enough room for the theoretically perfect answer. And it is a warning to every military in the world that values the appearance of capability over the reality of it. That strange, drag-inducing satellite photograph blemishing piece of carbon fiber beneath America's most advanced fighter jet might be the most consequential piece of aerospace engineering produced in the 21st century. Not because it is beautiful, it is not. Not because it is fast, it is slower than it should be, but because it keeps the aircraft alive long enough to do its job and return home with its pilot breathing inside the cockpit. And in the end, in the brutal and unforgiving arithmetic of warfare, that is the only measurement that truly counts. Not the specification sheet, not the design aesthetics, not the computer simulations that say everything should work perfectly. What matters is whether the machine survives the fight. The external gun pod ensures that it does, and the nations that understand this distinction will dominate the next generation of aerial combat. The ones that do not will spend their time admiring perfectly smooth fuselages that crack apart the very first time they are asked to do the one thing they were built to do. Thank you for watching. Thank you for thinking deeply about this, and I will see you in the next one.